Okay, so let's start our class. Sorry that I'm late. I apologize. What time is it right now? I cannot see the time. Okay. So what I'm going to do is I will start now. Maybe continue about half an hour or so. Then we can give about a 10-minute break, and then we will finish at 3:30. So, by the way, not much, many topics left. We will, I don't know if it's because of this online conduct of the class material, but it's going, and maybe, some part of the semester we use the whiteboard, some part of the semester we are using the slides. So it's going a little bit faster than usual. So most probably the topics will finish maybe next week, I think. So the course material, I mean, everything that we discussed in syllabus will be finished. And then we will see about the class hours after that. But so we are working on this final few topics. So maybe I can just summarize for you if I can write on the slide. Let me choose a pen. So we, of course, our topic is viscous flow. And for viscous flow, we first obtained, so the concept, we are focusing on the concept of the boundary layer. We obtained boundary layer equations. That's what we did first. And then we have seen Blasius solution. That's what we have seen so far. And then we have seen other, let's say, more generalized solutions. Including last week we discussed this, more generalized solutions. Generalized meaning not only flat plate, but other geometries, but still steady state laminar flow boundary layers. And now last week we also started talking about another solution procedure, which we call momentum integral method. So we started discussing this. We will continue that. And momentum integral method and related solutions, let's say. So we are here. And after that, we have one more topic related to turbulent boundary layers. I guess we will have enough time for that. So yeah, that will be basically the end of the semester. So whether it's going to end next week or maybe one or two, maybe one class last week, we will see how it goes. Okay, but so for the viscous flow section, everything until this point is covered. We are at this stage, and actually last week we started the derivation of this, which we call momentum integral equation. And I guess we were here just to remind you from last week. If you go back a few slides, starting from here, again, maybe one more. What we are after is obtaining what we call integral characteristics of the boundary layer. So what are the integral characteristics? All these parameters that we defined so far, like we are interested in the friction coefficient distribution. So therefore, integrating this, we want to get the drag coefficient, for example. We want to get the boundary layer height or boundary layer thickness distribution. We want to get momentum, the displacement thickness distribution. We want to get momentum thickness distribution. So all these are what we call integral quantities. And why do we call them integral quantities? Because we need if we know the velocity profile within the boundary layer, integration, using the definitions of these quantities, integration that includes the velocity profile gives us these integral quantities. So the idea was, instead of actually applying Blasius's method, meaning change of basically variables and defining a stream function, can we actually go through another way, which we call the momentum integral equation method? So for that purpose, our starting point is the same. meaning that if we can reach to a simplified equation, so I'm stating the objective why we are doing this, a simplified equation, again starting from the same differential equation set governing equations, we reach to a simple equation. So that's also, you can say, well, that's also what Blasius tried to do. He tried to reach a simple equation, but now the equation directly written for these integral quantities, like theta, for example, like delta star, for example. So that's the purpose. Can we reach one simple, if possible, ordinary differential equation written in terms of these integral quantities? So if I can solve directly one equation, and then the direct result that I get are the quantities themselves, instead of these f primes and everything. So our starting point is this, and we started working on these terms. I mean, integration of these equations. We started working on these terms one by one. For example, for the as we did last week, for the momentum equation. And by the way, here this is only x momentum conservation equation. Just to remind you again, the y momentum conservation is just giving us this dp dy equal to 0, if you remember from before. So we said, okay, what if we take this equation now, that is x momentum conservation, and just integrate from 0 to the height of the boundary layer. So h is some distance greater than the boundary layer thickness, let's say delta. Okay, so we have, you can see that we have integration signs in front of each term. Of course, then mathematically we have to work this out, because in order to understand how we can perform this integration. And so for example, so this is the same equation as in the previous slide. So like this, if we focus on different terms to make them more understandable, let's say, we discussed this also last week, the second term on the left-hand side. So we're talking about this term. Mathematically, we separated or decomposed it into two components, and then worked out some relations. For example, like dv dy is actually equal to du dx from continuity equation. And when this one is integrated from 0 to h, this will become equal to u h times the value of v at h, and stuff like that. And then we inserted this expression into this top equation here. Plus, we worked on this fact. This is basically making use of the continuity equation in integration, meaning that we are working on this term. So integration from 0 to h is equal to this, and we ended up with the fact that this is equal to minus vh, which means the value of the v component or the y component of velocity at distance h. So we said, and then, yeah, we replaced all of these terms into our original momentum equation, and then this is what we got from that point. This, I guess that's where we left off last week at the very last minute. So basically, when we look at here, we have one u du dx dy here, another one here. So just add them up. We get two of them here. We have two, and minus this term. And on the right-hand side, we have to integrate. We have to integrate the pressure gradient term and the viscous term. So that's where we were on last week on Thursday when we finished the class. So we continue to this derivation. Again, our ultimate purpose is to do whatever is necessary to come up with one single simplified ordinary differential equation written for unknowns, which are the integral quantities that we just talked about. So working out, for example, the last term on the right-hand side. So we continue here. Now we are talking about this term. And here, again, writing this as v times d of du dy, that must be integrated. And the thing is, du dy, that's the velocity gradient basically outside the boundary layer. If you are at h, outside the boundary layer, and the velocity gradient at the wall, basically at 0. So just to remind you how the velocity profile looks like, let's say this is a wall, this is my velocity profile, okay? So if we are outside the boundary layer, and by the way, this is y-axis, right? So if the, I don't know, boundary layer thickness is somewhere here, if you are outside the boundary layer, the profile is basically flat, okay? So if you're here, or when you're here, du dy is basically 0. There's no variation of u with y. But when this is why this term is 0. The other term is du dy value at the wall. So whatever velocity gradient we have here, we know that it is not 0. So that will go to this term. So, but we know one fact, this velocity gradient at the wall at 0, let's say, when multiplied with viscosity, that is equal to wall shear stress, which is actually written here. Yes, we call it tau wall. So this v times du dy, I'm sorry, the du dy at 0 is actually equal to wall shear stress. This is one thing. The other thing is this term now. If we talk about this term, this is related to pressure gradient along the body. So along the flat plate in streamwise direction, as you can see, dp dx. But if you remember from Bernoulli equation, we previously showed that this is actually indeed related to, or it can be replaced with this term here. So minus UH times DUH over DX. This comes from Bernoulli equation, which we showed previously last week. Taking derivative of the Bernoulli equation with respect to X, that's what we get. So now what we can do is, okay, why don't we replace these two terms with this? So UH, DUH, DX, use that instead of the pressure gradient term, and use tau wall basically for the second term. So when we do that, so we end up with rearranging the equation here. Basically, we end up with this term. So we have to integrate these three terms in parentheses, and on the right-hand side, that must be equal to minus tau wall over rho. And what do we have inside this parentheses? So we investigate this. First of all, we have 2 times u du dx. Mathematically, this is equivalent to du square dx. I mean, taking the derivative of u square with respect to x. So this is mathematically the same thing. And the second term, uh times du over dx, can be written like this. It's basically the derivative of uh times u minus u du dx. So we make use of that. And then we insert this into our equation here. So we get these 2 separate integrals on the left-hand side. So the integration of d dx uh minus u dy. This is the first integral that needs to be taken now. And the second one is related more to the uh variation with x. So this needs to be integrated, and both must be integrated with respect to y. Our integration variable is y. So we will take that into account actually here. So for example, why did I say that? The explanation is in the next slide, but let me explain it here. Since we are integrating with respect to y, we should ask this question: which of the terms here that we are seeing are actually functions of y? Okay, if they are functions of y, they should remain in the integral. If they are not functions of y, they can get outside the integral. So that's why integration and being aware of the fact that the integration is only being performed for y is important. So when we take that into account, so for example, the derivative with respect to x is by default independent of y. So we can take it outside the integral. And in the second term, we know that UH variation also is constant at any y location. So what do I mean by that? If we are talking about like a flat plate problem, there could be, so this is our x coordinate and this is our y coordinate. So along y direction, so if this is our boundary layer, at different x locations, we could have different UH values. This is fine. So UH is a function of x. But at any x location, at any fixed x location, we have one UH value. That UH does not change with y. So that, which means that we can take this term outside the integral. So we did that here, as you can see. Okay, then in this equation, there's also one thing that I would like you to notice. For example, we have terms like u times UH minus u. Here I have term like UH minus u. Why should we why should we pay attention to the existence of these terms? Well, the reason is that they are familiar because we saw them before. Where did we see them? Well, we saw them in the definitions of these integral quantities that we introduced before, like delta star and theta. Like the definitions are written down here, as you can see. We have delta star definition. So here, especially if it's an incompressible flow, these rows cancel out. So I end up with this this term here. Well, I indeed have a UH minus U term here. So which I see, for example, here. So this must be related to delta star. Similarly, for momentum thickness that we defined before, I have a U, as you can see, U minus UH minus U, which I see here. So this must be related to momentum thickness, okay? So, which means that I can, you know, these integrals are actually related to displacement and momentum thickness terms, which are indeed parameters that I'm interested in. I am interested in finding those parameters after, if possible, by direct integration of some equation. So making use of this, making use of what? Making use of these definitions of delta star and theta, displacement thickness and momentum thickness. So we make use of it we just use them to come up with this equation. So the first term looks something like this: d dx of now UH squared times theta. Now we directly see theta in our equation. In the second term, we see UH DUH dx times delta star. So we directly see this delta star plus, nice thing, I see tau wall on the right-hand side because, you know, tau wall, therefore related to that CF, friction coefficient, and related to that CD is basically another parameter set that I'm interested in. So this is basically, as you are seeing in front of your eyes, this whole thing is now transforming into a single equation, which is basically written entirely as these integral boundary layer quantities as dependent variables in the equation. Good. So after this, we do some manipulation to make it look better a little bit. So dividing by UH square, we get this form of the equation, and introducing the definition of friction coefficient. So instead of tau wall, after dividing by UH square and multiply, there's already a row here, and basically if even multiply this by 2 or divide this by 1/2, I get CF in the picture. So if I do that after these few rearranging and reorganization of the equation, we get the well-known in aerodynamics or in fluid mechanics, the well-known momentum integral equation. Sometimes this is also known as Karman momentum equation. This equation has one new variable. Well, you cannot see it in the equation, but the definition is given on the right-hand side. First of all, let's check term by term. First term is the derivative of momentum thickness with respect to x. So entire equation is written by in terms of these integral quantities. Second equation, I have theta again, momentum thickness, plus I need to know how u edge changes. For example, if this is a flat plate problem, this second term will be 0 because u edge du edge dx is 0 for flat plate, like Blasius type solution. And plus I have this term. Now I have a new term, which is the ratio of delta star to theta. Okay, in fluid mechanics or in aerodynamics, we call this term delta star to theta ratio form factor, or sometimes we call it shape factor. You can see both nomenclature. H, we use the capital letter H for this. We call it the shape factor or the form factor. So this is also an integral term. And on the right-hand side, we have the friction coefficient, which is also nice. But there's one problem. First of all, yes, this equation, the one that we just discussed, as you can see, all the derivatives are only dependent on x direction. So there's no y dependency. So therefore, we can directly write as an ordinary, using ordinary derivative. So it becomes actually an ordinary differential equation, first of all. So the question is, what are the unknowns here? Well, the unknowns are the integral quantities of the boundary layer. So unknowns are like theta, one unknown, h, or therefore delta star is another unknown, and CF is another unknown. So we indeed have three unknowns here. The UH value at a certain x location or the UH gradient is known. So this part, theta is an unknown, this part is actually known. And what do I mean by known? Well, I can even obtain this from an inviscid solution. Like if you are interested in, for example, solving this equation to get the boundary layer characteristics over an airfoil, for example, or a wing, what you can do is first obtain a panel method solution for this airfoil, and the velocity field that you will get as a result of the panel method will be your UH distribution, UHX distribution. If you take its derivative, you get the due over dx. So this is assumed to be already obtained from an inviscid solution, means this. Yes, so the problem is we have three unknowns and one equation. Okay, so what are we going to do about this? Because this is only one equation here. So, of course, in order to solve this equation, we need to know the velocity profile. So velocity profile, U, means that variation of especially streamwise velocity U with Y coordinate. So we do not know that function. So if this is some kind of solid surface, we would like to know this function. I mean, normally we want to solve for this function, but that does not appear in our equation. So if we somehow knew this function as it is written here, we could obtain a solution for this, because knowing U profile means that I can actually have values for theta and delta star, and having CF. So it's kind of, let's say, a dilemma here. I mean, as it is written in the second bullet point, if we knew UI, why would we even need the integral approach? Okay, because what we, as it's written here, what we need to know is indeed this velocity field. That is the ultimate result that we are after, velocity variation within the boundary layer. So, but the nice thing is this: what we can do, or the people who developed this method thought, okay, we do not know UI, but what we can do, and I mean, let me first explain what we can do, or the strength of this method is this: we can assume certain profiles, I mean, certain mathematical functions that can potentially represent the velocity distribution, and then solve and then apply this and find the momentum integral equation and apply that. Okay, this kind of approach is more generalized compared to Blasius's approach, because you can apply this momentum integral equation. It is not going to be constrained with laminar boundary layers. You can directly apply it to turbulent boundary layers as well, as long as you have a good mathematical assumed function, and you can test that if it's good or not after the application. And you can apply this methodology to any kind of boundary layer, not only flat plate or not only laminar boundary layers. Some examples, so we will see that in the next slide. So first example, let's say consider the flow over a flat plate. So our U edge distribution, basically there is no U edge distribution along X. It is equal to a constant value, which is the free stream velocity, U infinity. So du edge over dx is actually equal to 0 in that integral momentum equation. So when we do that, it gives us this relation. The momentum thickness variation must be equal to 1 over 2 CF variation. So theta is a function of x, CF is a function of x. So the question, then we say, okay, let's guess the velocity profile. Okay, or as it is kind of explained here, let's guess the crudest, or let's say the most, most, let's say, rough or very crude velocity profile, which is basically a simple line, simple linear line. But absolute minimum physical criteria must be satisfied. What is that? We need to satisfy the no slip condition. If it's just, and we are assuming that it's a, let's say, straight velocity field, and at y equal to delta, it's going to be equal to, the velocity is going to be equal to UH. So U over UH, so this equation tells us. So these two conditions are satisfied. We just do not know how it changes between these 2 points. We say, okay, let's assume it's changing linearly. So we just put a straight line. So when we do that, so we obtain some relations, obtaining displacement and momentum thickness in terms of delta. So delta star over delta here, I mean, from their definitions, we have delta star over delta. We obtain delta star over delta is equal to 1 over 2. So in this very specific case, flat plate boundary layer with no pressure gradient, therefore, delta star must be changing with half of what delta is, and momentum thickness should be changing with 1/6 of what delta is. So this is the result that we get from assuming a linear velocity distribution. And the tau wall shear stress, which is given by this equation, mu times UH, which is all given as a ratio of delta. Therefore, CF can be obtained and all of that. Then if we plug in this equation now, momentum integral equation, let's see what we get. Momentum integral equation says that d theta dx must be equal to CF over 2. So we have therefore d theta dx is d delta dx. So this is because this is 1 over 6. So 6 is here. And CF is 2 nu over delta over UE. We put it here. Then we need to integrate. So we take this delta to the left-hand side and dx to the right-hand side. And then we obtain this equation. Delta, d delta is equal to this. And let's see what we get here. So the boundary layer thickness is then estimated as this equation. So we have an integrated equation here, delta square over 2 is equal to this, and we take delta out, square root of 12 nu x over UE, and we reorganize. We have basically a Reynolds number definition here. So square root of 12x divided by square root of Reynolds x, and then we get this relation. Interesting, very interesting relation. Why is it interesting? Let me explain this, and we can give a break. We get the delta x variation, 3.464 times x over square root of Reynolds x. What was this? What is the solution for? Let's remember that. Solution for a flat plate boundary layer. So solution of exactly what Blasius was trying to do. This is our flat plate, boundary layer growing on top of it, laminar flow, steady flow, incompressible flow. Blasius solution, Blasius obtained a solution for it using its own methodology. This method, which basically we obtained this relation by assuming a linear velocity profile, gave this equation. Let's compare them. The Blasius solution gave this for delta, 5 times x to the Reynolds x square root. This very crude approximation of assuming linear relation gave us 3.464 times this. So this means that this very crude approximation, first of all, without going into all complex Blasius mathematical solution, gave us a quick result, which is different than Blasius's more correct solution, but it's not that bad. It's a little, this coefficient is a little bit lower, so meaning that delta that you will be estimating by assuming a linear variation will be less than the more realistic value of Blasius. So how much less? You can compare these two coefficients. So 3.46 over 5. If one of you can calculate this number, I can tell you how much less estimation it's going to be. I don't have my calculator right now.
0.69.
0.69 approximately. So it means that this simple linear velocity assumption results in about 30% less prediction of boundary layer thickness compared to Blasius. Okay, well, is it good or bad? Engineering judgment, we have to decide. Similarly, we have all these, but I want to discuss all these also in detail. Anyway, so let's give a short break at this point. It's 2:48. Let's meet at 3 o'clock. I don't know, maybe it's not a short break, but okay, let's meet at 55. I don't want to lose, we already lost some time because of me today. But so let's meet at, in 7 minutes, okay? So we will continue from here. So assuming this linear velocity profile, let's check out the other parameters like momentum thickness. So you can see momentum thickness is also different, but it's I guess less than 30% if you just divide 0.577 by 0.644. It also under predicts, I can say under predicts
11%.
11%. Thank you. 11% difference. So 11% under predicts the Blasius solution for the flat plate flow problem. Similarly, also for CF. Anyway, CF, the friction coefficient is indeed directly related to momentum deficit, the momentum that we lose right inside the boundary layer. Because of the momentum that we lose, that comes back to us as drag or friction. So therefore, similar to that, CF is also under predicted the same amount ratio. Surprisingly, delta star is quite close. Delta star is very slightly over predicted. So if you remember, delta star is basically was related to the mass flow conservation. And regarding the shape factor, H, the linear velocity assumption a little bit over predicts the shape factor compared to the Blasius's solution. Well, you can see that this kind of, I'm using momentum integral method indeed can be useful, but we need to, of course, as you can see, we need to find, I mean, it's nice that it's more generalized, and we will make use of that fact when we are going to be dealing with turbulent flow boundary layers, turbulent boundary layers. But in this case of laminar boundary layers, that is how it works. Of course, you can say, well, maybe we can assume a better function than a more generalized function than a linear distribution. Well, that is indeed true, which is actually what Polhausen did in 1912. So we will talk about that a little bit. For that, I need to share my other presentation. Let me stop this one and open. But just a second, I have to get out of presentation mode here. Yes. And share this one. Okay. I guess you can see the slides again.
Yes, sir.
So the idea is, okay, let's not do that. Let's not assume a linear function. We know that it is not realistic, although it's not too bad. For some it can be bad. I mean, if you think about it, for the very simple case of laminar flow over a flat plate, the CF, therefore drag, will be under predicted more than 10%, even for that simplistic case. So this means that if you go for more complicated cases like a flow around an airfoil or a three-dimensional wing, we cannot do that. I mean, we cannot assume a linear velocity profile. So Polhausen thought, okay, let's assume a more generalized, here in this slide says more realistic, but I would say more generalized velocity profile than a linear one. So he assumed a polynomial, basically a fourth order polynomial with unknown coefficients. So assumed for what? Assumed for the velocity profile. So on the left-hand side, we have u over ue, this one. And on the right-hand side, this is written as a function of y over delta. So this is something that we want. But as a polynomial, fourth order polynomial, so we have 5 unknown coefficients here, a, b, c, d, and e. So first of all, we need to determine what those coefficients are, and then do all the integrations and everything to see, to obtain the variations of delta, delta star, and theta, and therefore h with respect to x. So we have 5 unknown coefficients, and these in reality unknown coefficients can be estimated as a function of some parameters based on the boundary conditions themselves, which means that, first of all, okay, Polhausen, you can go ahead and assume a fourth order polynomial, but physics tells you that, okay, hold on for a second, this cannot be any fourth order polynomial. This fourth order polynomial that you assumed must obey, first of all, must satisfy the boundary conditions. I mean, first of all, for this to be, you know, a realistic, let's say, realistic function, so that is good, that can represent the physical velocity profile. So it should satisfy boundary conditions. First of all, yes, the no slip condition. So at y equal to 0 on the wall, u must be 0, first of all. Second, as expected, at y equals delta, edge of the boundary layer, u must be equal to uh. So these two are straightforward. Now we work on another 3 more boundary conditions here. Because we are kind of assuming a random function, basically. I mean, some kind of fourth order polynomial. At y equal to 0 again, on the wall, if we write down the momentum conservation equation, on the wall, we know that there is no slip condition, u equal to 0, v equal to 0. So the momentum conservation equation, these two terms automatically becomes 0 at the wall. It says here for a fluid element attached to the wall. Then this is on the left hand side is 0, right hand side we have the pressure gradient, and we have the second derivative of the velocity profile. Since we assumed the velocity profile as basically a random fourth order polynomial, this condition tells us an important, or gives us an important message. It says that, well, you cannot just assume a random fourth order polynomial. If you take the second derivative of your assumed function, it must be equal to 1 over rho dp dx, or it must be equal to, we know that from Bernoulli, we discussed it in the previous hour as well, times or minus times duh dx. So this second derivative of your assumed function must satisfy this condition at the wall. Okay, so this is kind of also another boundary condition that assumed function must satisfy. What else? At y equal to delta, so at the edge of the boundary layer, as we have discussed in the previous hour, actually both of these cases must be satisfied. The first and the second derivatives of the function that we assumed must be equal to 0, because we are expecting, I mean, you know, if you do some experiments over a flat plate, for example, we are expecting a functional variation like that. So outside of the boundary layer, or at the edge of the boundary layer, or let's say above the edge of the boundary layer, we have a basically flat uniform distribution, especially for example, for a flat plate problem. So this means that there's no variation in u with y. U is not a function of y anymore if you are above delta. So both derivatives must be equal to 0. The question is this generalized function, does it satisfy all these conditions? Physically imposed conditions, that's how I can express them. Physically imposed conditions. Well, of course, the answer to this question is, well, it may or may not satisfy those conditions. It totally depends on the values of these 5 constants. So which means that I can actually use those conditions to find proper values of these constants, so that it can actually be a realistic, or it can actually represent a realistic velocity profile. First of all, in terms of the shape of the function. Okay, in terms of the shape of the function. Okay, so and of course, I think I should stress this point again. What we are doing at this stage, we are not solving any equation right at this point. We are just assuming a shape, this one, a shape. We don't know if this shape satisfies conservation of momentum, whether it satisfies continuity. We have no idea. We just assume a shape. But that shape, and then we say that, okay, I don't know if this satisfies any of the conservation equations, but first of all, I need to make sure that geometrically it satisfies some conditions. It cannot be any random shape. This cannot be for example, the shape of an apple, or this cannot be the shape of a flower, right? This should be a specific shape. So so we use these restrictions basically to find that to make sure that function generates that specific shape. The next step will be to check whether this function actually satisfies the other physical conditions like conservation equations, for example. Okay, and in reality, this is the main idea behind this momentum integral method. Good, so based on this, we start working on our equation. Not all of them are listed here, but the original assumed function is here. Fourth order polynomial. So we say from the first boundary condition, yes, at y equal to 0, velocity will be equal to 0. So all the terms disappear except a. So a must be equal to 0. We get that from that. Plus the second boundary condition, what was that? At y equal to delta, u is equal to uh. So when we write that, so when we insert delta, so this y over delta values all become equal to 1. So basically, and u is equal to uh, so left-hand side is also equal to 1. So we get 1 equal to this b plus c plus d plus e. So we get one equation from it. By the way, we need 5 equations to solve the full set, and we have 5 conditions. But in these slides, not all the conditions are listed, but you get the idea. For example, from the fourth boundary condition, what was the fourth boundary condition? At y equal to delta, du dy is 0. So we get the derivative of this function with respect to y, force it to be equal to 0. We get another equation. So this is our third equation between a, b, c, d, and e. And we have 2 more. We have like the third boundary condition, which is imposed on the second derivative of the shape of the function. And we have also another imposition again on the second derivative of the function, but at y equal to delta. This was at y equal to 0. So when we do all of this, so we get values for these 5 coefficients. Again, I'm repeating this. Okay, let me first discuss the values. A is equal to 0. B must be equal to this 2 plus lambda over 6. By the way, the definition of lambda is here. It's a function of delta square over nu and the UH velocity gradient. This is in fact known as Polhausen's pressure parameter because it's related to the pressure gradient. C is equal to, and by the way, this lambda, where is it coming from? Basically, it's coming from this third condition, because third condition says the second derivative of this randomly assumed geometry must be determined by the edge velocity. So this is where it's coming from. Anyway, so when we do that, so B is equal to 2 plus lambda over 6, C is equal to minus lambda over 2, D is equal to minus 2 plus lambda over 2, and E is equal to this. So therefore, we have now some expression, some expressions, I guess that's the correct word, that we obtained for all of these 5 constants as a function of I mean, when I say constants, of course, I have to explain it a little bit more carefully. They are constants of the polynomial. Yes, that is fine. But how do I calculate those constants? By basically they are all dependent on lambda, except for a. They are all dependent on lambda. A is 0. Well, and what is lambda? Well, lambda depends on two things. First of all, the UH, velocity gradient. So this is a function of x. And delta, which is also a function of x. So at any fixed x location, so if we are basically talking about this boundary layer growth over this object, at any fixed x location, we have a constant value for lambda. At that location, delta will be a constant, UH over UX will be a constant. So at a fixed x location, all these polynomial parameters will have indeed constant values, so that but constant, but now physically meaningful constants, so that shape is actually relevant to real life application. But I know that if I go to another x location, these constants will change. So if I go to a downstream location, constants will change. So therefore, my velocity profile will be different in terms of its shape. Okay. So now the next question is, I mean, once I have this, I mean, if I get UH over UX again from an implicit solution, once I have this, this means that this fourth order polynomial can indeed give me realistic looking velocity profile shapes. So I satisfy my first important condition. But the second condition is that is a velocity profile like I just found, does that actually satisfy conservation equations? So in order to find that, now I have to invoke this momentum integral, because this momentum integral equation is indeed a combination of basically continuity and momentum conservation equations reduced to one single ordinary differential equation. So now I need to know the second part, or I need to I shouldn't say no, but I should say I need to start making use of the second part, or invoke the momentum integral equation. So in order to do that, we need to do some mathematical manipulations to make the equation look a little bit better. Equation meaning the velocity profile definition. So generally in Polhausen's approach, which he did in early 1900s, so we denote y over delta as eta. Okay, so we call it eta, and u over ue as f. This, so we call it as f, okay? And we just write everything like that. So f on the left-hand side will be equal to this, 2 eta minus 2 eta cubed plus eta to the 4, and lambda times all these parameters. After rearranging and using this value as the definition of lambda. Okay, so we have this function now. We generally divide it into two parts just to make it look better. Again, the first part, we call it capital F eta. And the second part, I mean, the multiplier of lambda, I can say, is called G eta. But don't get confused, because this is just, we are just giving some names, that's it. So if we investigate now this lambda a little bit here, generally, and it says here under normal conditions, we can obtain a solution if lambda value is between minus 12 and 12. And the reason is explained in the next slide. But there is also a physical reason. The choice of lambda determines the shape of the velocity profile. And if you use in this equation, this is your velocity profile shape, yes? This, for example, here, this is your velocity profile shape, f versus eta. F was, again, remember, U over UH. This axis is U over UHF, and this axis is Y over delta, eta. So these are your several velocity profiles. If lambda is greater than 12, here, as it's written here, the solution starts penetrating the wall. So meaning that penetrating the wall means at the wall, we end up with a zero gradient at the wall. So du, dy becomes zero at the wall, which, if you remember from our previous discussion last week, that indicates the case of flow separation, starting point of flow separation. On the other end, on the other limit of this, if lambda value if it is less than minus 12, then solution is not physical anymore. It starts overshooting, which means that U will be larger than UH, so which is of course not realistic, because that doesn't satisfy our physical condition, first of all. So this is mainly basically due to, as it's written here, due to the fact that approximating the velocity profile as a polynomial. But by the way, right, you can think that, I mean, nobody told us which function to use for the velocity profile. We first used linear, and we said we have seen that there are sometimes significant differences even in the simplest flat plate boundary layer case. Then we said, okay, let's forget about that. Let's use a polynomial. But is this the best choice? Probably not. And in fact, that approximation of the boundary layer as a polynomial satisfies, as it's written here, satisfies some but not all of the boundary conditions of a real velocity profile. So we have to be careful, therefore, about our lambda limits. So separation I guess this must be plus 12, separation or unrealistic profile shape. So we have to be careful about that. As I was just describing, flow separation is defined by this: du dy at the wall is equal to 0. So we know that, which corresponds to f prime at 0 is equal to 0. By the way, this f prime is not the same as the one in Blasius. It has nothing to do with that. It's totally different. Okay, so don't get confused. It does not refer to the same parameter in Blasius solution. So this is important. But anyway, our physical condition for separation detection, I can say, is the velocity gradient at the wall must be equal to 0. So f prime 0 will be equal to this, and you will get a value. In fact, the minus 12 value is coming from that. So therefore, coming back to now our, I said this kind of approach, meaning what is our approach? 2 steps. Where's my pen? 2 steps. First, assume a velocity profile function, but make sure it is indeed not any function. Make sure it's at least satisfies some of the boundary conditions. Plus, second step, check if this kind of velocity profile, or check what is required for this velocity profile to satisfy the momentum conservation. Check if conservation equations are satisfied. How do we do that? For that purpose, we go back to our definition of displacement and momentum thicknesses. So we say, okay, here is our delta star. It needs an integration from 0 to delta of this term. In this term, U is our fourth order polynomial with those given coefficients. So we assume that now. We plug that in, And by the way, this U over UE, we called it F before. And this, when we multiply with delta, this variable becomes eta. So it becomes equal to an integration from 0 to 1 delta times 1 minus f d eta, and f is this function over here. This whole thing here is the f function. We put it in the integral and then integrate, we get this one. It's integration from 0 to 1, by the way, because eta is y over delta, so it changes from 0 to 1. So doing that integration gives me a value for delta star 3 over 10 minus lambda over 120. Similarly, I do it for theta. So this time now I have f times 1 minus f. It gives me now this function. So as you can see, these compared to the linear velocity profile approximation, which is very crude, obviously, I get a little bit more sophisticated representation for delta star and theta. They are at least functions of lambda, which is a function of the pressure gradient. So now we consider the integral momentum equation, which we derived before. So this is our integral momentum equation. And here, reorganization of the equation a little bit. Reorganization meaning multiplication by this gives me that equation. Instead of tau wall, I have this, it is basically here, and viscosity is basically as mu over rho went to the left-hand side. So here we define a variable, capital lambda. It is theta square divided by nu times the UH velocity gradient, and insert this into this equation. We get this equation UH times d dx of capital lambda du dx, and all this function. So this capital F lambda and capital F, F1 lambda, and capital F3 lambda, but these are capital lambdas. So this is just a mathematical organization. The functions are written here. F1 is basically your delta star over theta. Okay, and of course, regarding Paul-Hauser's method, this needs the integration. And F2 is theta over UE times your wall shear stress, or wall velocity gradient, actually, function of lambda. And F3 lambda function is this big function over here. There are some more details, but I'm running out of time. There are some more details which we're going to cover from this point, and which we're going to continue from this point tomorrow. But I guess you get the idea. The idea is now to find, using the integral momentum equation by using these lambda definitions. Now we try to find a good, a specific solution for this integral momentum such that this integral momentum equation will be satisfied, in addition to the fact that our shape function assumption geometrically is also making sense, a reasonable representation of the velocity profile. So you can see this kind of approach, Paul-Hauser's approach is a little bit more involved than Blasius's approach, but still there's one big limitation. That limitation is that still we are constrained within the domain of laminar boundary layers in case of Paul-Hauser's solution. It is indeed can be modified for turbulent boundary layers. But in order to understand what turbulent boundary layers are, we need to learn. We will actually start discussing, we will start from the basics of some turbulence physics. We will learn a little bit more, and then we will see when a boundary layer becomes what we call a turbulent boundary layer, what kind of changes do we actually end up with? What kind of changes in velocity profiles, in flow physics? and how do we actually solve that problem? How can I obtain a solution? How can I obtain the integral quantities like delta star, delta, and theta for a turbulent boundary layer? That is coming very soon. I think tomorrow I would like to finish this Polhausen method quickly. Then I guess we will start slowly going into this turbulent boundary layer discussions. Very good. Okay. If you have any questions, we can start discussing for a few minutes.
Can I ask a question?
Yes.
Do we treat the Blasius equation as the exact solution for this case? I mean, comparing with the approximations.
Yes, I mean, for a steady incompressible laminar flat plate boundary layer, yes.
Thanks.
Mm-hmm. All the rest, as you said, all the rest that we discussed are approximations. Any other question?
Hocam, in this solution, because we have only 5 boundary conditions, we defined the 4th order polynomial. Mm-hmm. This is the maximum order, right? I mean, we don't have 6 boundary conditions in this flow.
Let me try to explain it like this. I mean, Polhausen assumed basically 4th order polynomial, so that there are 5 unknown coefficients which can be determined by 5. Here in the slides it says boundary conditions, but I would more say geometrical conditions, I guess, because they constrain the shape of the polynomial. I mean, the term boundary condition is more relevant when you solve like equations, conservation equations. Here we are not solving conservation equations. So I would prefer to say like geometrical constraints, maybe I should say. So if you choose more than 4th order, you could have trouble in terms of constraining your geometrical shape. Okay, because these 5 physical conditions are basically the generalized, the most general geometrical constraints that you can apply to this function in the context of the boundary layer physics. Okay.
I see, Hocam. It means that if I want, for example, a 5th order polynomial, I have to define new boundary conditions by myself.
If possible, yes, if you can. I'm not sure if you would be able to do that, but yes, you should do that, because otherwise your the function that you assumed must be constrained. Otherwise, 4th order polynomial can look like anything, right? And you can make it look like, I mean, go to Excel, try to draw a 4th order polynomial by playing with the coefficients. You can make it look like anything. So, but here, the boundary layer physics is the constraint. Constraint on what? Constraint on the shape of this function.
Hocam, can I ask a question? What if we try to make a polynomial more simpler by getting, let's say, 3rd order polynomial? Which boundary condition we can have must to do? Which one can neglect it?
First of all, I guess the first 2 must remain. We cannot get rid of them. If you remember, we used the first 2 only when we assumed linear velocity profile. I mean, linear velocity profile is basically a 1st order polynomial, yes? So we have 2 unknowns, 2 coefficients basically. So we need 2 conditions. So we used the no slip condition and we used the second condition here. So if you go, as you said, if you take a 3rd order polynomial, probably I would say you should use the 4th condition. You should impose the fourth condition. As you see, whatever you do is an approximation. And because of that approximation, even this fourth order polynomial can not represent the physics fully. That's why we end up with problems like this. I mean, problems meaning limits on lambda and stuff. Yes? So, yeah, I guess that's how I can try to explain it. Okay?
Yes, sir, thanks.
Okay, everyone. So, thank you. So we'll meet again tomorrow. Let me stop sharing and stop the recording. Herkesle o zaman yarın görüşmek üzere.
Görüşürüz hocam, kendinize iyi bakın.